So the talk is Wololo. The name comes from the Age of Empires game, where there is a character, a monk, where you can create this character, and he starts converting the units from the other team. So basically, can convert units from the other team. And this is a parsing library I'm writing with a friend of mine. And so the idea is that you're writing a parser, you're using one language to absorb code written in another language. So that's where Wololo, you're converting things and dealing with transformations. So that's where then the name comes from. And it's just a little joke because the monk sounds funny. And we are using Noam Chomsky's the linguist hierarchy for this talk. So if you see type 0 language, that means a Turing-Complete grammar, where you need a Turing-Complete system to be able to parse it. So an example would be C++, where the grammar is Turing-Complete. So you need something Turing-Complete to be able to understand the language in semantics, in terms of semantics. A type 2 language would be a context-free grammar, which are most programming languages, where you can just use Backus-Naur Forms, BNF forms to be able to parse it, to break it down. Just to give you where this is coming from. So this is the overview of the talk. I'm going to be talking about us briefly. There was a disclaimer, I dropped it. So what is the project? About the Lisp programming language. It's a bit of a weird language, so I'm going to touch upon that. Then I'm going to talk about BNF, which is the standard way you write grammars, and then you feed that into a parser generator, like Yak or Bison. Then I'm going to talk a bit about a few libraries that already solve the limitations of BNF. They already exist. Then I'm going to talk a bit about our approach and where we ultimately want to end up, and then we'll have some time for questions. So about us, I'm Martin. I work on the packaging team. I am a package maintainer. I maintain LibreOffice, Apache, a bunch of other stuff, BCP. And I'm mostly interested in, outside of like the day-to-day work, in programming language theory, Lisp as a family of languages, and assembly language. So those are the two things that give me the most joy when I'm writing them or reading code in assembly and Lisp, which are on both ends of the spectrum, very low level, very high level language is Lisp. And João Pedro is a friend of mine and also works at SUSE, and he's a customer support engineer. And he's a tech enthusiast, and he works on, he's curious about operating systems and software in general. So what is this project? It's a work in progress library written in Clojure, right? And so the idea really is that we're going to be able to use this library to write interpreters, compilers, but mostly I'm focused in writing semantic analysis tools like linting tools, any kind of thing where you have to convert the code into a tree and then do some analysis based on that tree, on the semantics. This is the tool to do that. Should be a great tool to do that. So it's really, really focused on giving you a good developer experience so that you don't have to study too much theory. It should be kind of easy to get started. It should be like the Python of writing parsers, like something that you can sit down in one afternoon, have a good grasp of how it works, interact with the system, and just play around with it. And it's also like an educational framework. If you don't know too much about parsing, you should be able to read the documentation, understand the library, and you kind of come to terms with how parsing works in general. And the way we develop it, it's kind of the way I develop my software in my personal time. I use TDD pretty much for everything. So there is not one branch of the code that doesn't have a test case already in advance. And it's mostly functionally pure code. So even though it's not Haskell, we're kind of abiding by those rules of functions don't mutate state, pure code. And the side effects and impurity, if there is anything, they're all isolated in one place. And so that's how I develop most software in my personal life. And then TDD kind of plugs into functional purity really well because you're just giving input, output, input, output, input, output. It's kind of easy to do TDD when you're just dealing with data directly, at least for most of your code. So this is one example of just two parts of a spec file for Vim, the Vim package. And this, if we look at a spec file, and I'm just plugging the talk into the real world, because like, what's the purpose without a real world example? We have some macros, like the conditionals. Every time we have the definitions there, we have to expand them. So we're really dealing with three languages in a sense. We have stuff from spec files that are already there, and you don't have to evaluate them any further. We have the macro definitions that we have to expand to kind of render them to something concrete. And then we have bash. We have like built-in shell stuff going on in the spec file. So semantically, we kind of have to think about it. If you don't know what the macros and the stuff is, you have to get to understand what it is somehow before you can make decisions, right? And bash is like embedded in the spec file. So you kind of have to switch into, oh, now I'm writing a bash thing in the language. And so when a tool like Spec Cleaner or RPM Spec, when they come here and try to make sense of this, they optionally would break this into a tree that encapsulates all these nuances of I'm dealing with bash, I'm dealing with macros, I can expand the macros and deal with really three kind of things at the same time. So this is kind of our real goal, is writing a parser library that can handle sub-languages beautifully and that we can use to power a generation of tools in the future. So I'm going to talk a bit about the language just because it's kind of different and uncommon nowadays, unfortunately. So it's a family of languages, really, written by John McCarthy, who was a computer scientist working at MIT. So when I say Lisp, I don't mean one specific Lisp, I mean the whole family. And it pioneered many important concepts like garbage collection, dynamic typing, conditionals. So before, if you look at Fortran 57, what you have is like jumps, a label, a go-to, and you just jump to a label. You do very procedural code. But Lisp had cond, which is like something that you can use to build an if. You can have proper switch semantics. And it introduced higher order functions, so you can create a function, return a function, take functions as input. This comes from lambda calculus. And it blurs the line between compile time and runtime computing. So Lisp has compile time at least since the 70s, where you can write code, run code at compile time. You can also obviously run code in runtime, and you can also compile code in runtime, which is weird because the compiler is embedded in the elf that you get when you build a common Lisp program. For example, you get a huge elf, but the compiler is in the elf, so you can still compile code during execution, and it will allocate pages, mark them as executable, do a lot of magic to get that to work. It has a super powerful macro system since the 60s, 70s, hygienic macros that Rust has. Lisp has had them since 1975 or something. And it introduced the read, evaluate, print loop that JavaScript uses, Python uses, lots of languages use. So Lisp has the REPL since its infancy. So just a bit of a story. We talk about live patching a kernel nowadays, like live patching is a huge thing for us in Linux. There was a mission in 1998, I think, 1999, and Deep Space One from NASA, and they were running a satellite millions of miles away from the Earth, and it was running Common Lisp code, and they live patched that code running in the satellite. So it's sending code through the universe, and you're just like live patching that. So that's a cool kind of use case where live patching is really relevant because you want to fix a bug on a remote system. And we are doing it across countries, and they're doing it across the universe. And to do this like 25 years ago is quite daring, let's say, quite impressive that they were able to do that. We kind of have to recreate a lot of machinery in C to do that kind of stuff nowadays. Just which comes kind of natively to Lisp. So I'm going to talk a bit about the semantics of the language. What you have here is S expressions, and the whole language is like very little syntax and very heavy on semantics. So it's all semantics, really, in a sense. In a sense, what you see in Lisp code is you have the syntax tree. That is your code. You're not thinking code in terms of lines. You're thinking code in terms of nodes in the tree. So here we have, for example, a plus and 1, 2, 3. That's the function name, and the rest are the arguments. And so when you say plus 1, 2, 3, it's going to sum 1, 2, and 3 and give you 6. And that's basically how the whole language works. You have the operator at the beginning, the function, the symbol that you want to find, and then you have the arguments, and then you evaluate that. So here we have an example of doing like functional application. We have an increment function, takes a number, just returns it +1, increases it by 1. And then if we apply that to a vector, that's not a list, that's a vector. The difference is that a vector is not evaluated, it's just a data structure. Then you get 2, 3, 4, 5. You apply that inc to the whole thing. And here we are defining a function. So we have defin for define function, and square, just the name, a vector with a parameter. So you have like x, and then you say x, multiply x by x. That's your square function. So you can kind of see how you can, if you learn the syntax, which is very light, you can kind of just, it's all semantics, and then you can you don't have to fight the syntax later. It's like it's done. You're done. Operator precedence is no problem. You never have to think about operator precedence in Lisp because the precedence is encoded in the list. So there is no struggle between operator precedence. There are no rules for that. You never hear Lisp programmers talk about that at all because it's gone. We solve that in a different way. And then because there are so many dialects of this language, and the community is kind of fragmented, I try to find the common feature of all these dialects, like the Proto-Indo-European of this thing. And in my view, it's all the code should be represented by the literal data structures of the language. So you have Lisp code should be, lists and maps and sets and literals. So that's how you represent your whole code is data literals. So if a language has its code represented as just data literals, it may become a Lisp at some point. And then all code being represented by these data literals, you can simply treat them as a data literal, and you don't have to evaluate it right now. So you can quote a list, and that says, don't execute it as code, just treat it as a list. And then you can manipulate that list, pass it around, and evaluate it later at any point you want. So you have lazy evaluation built into the language because you can just halt a piece of code and don't use that right now. Let's capture it and return it, do whatever you want with it. So here is an example. I'm going to increase the pace now. Say we have a list, just a list that's not going to be evaluated, and we assign that to the symbol form. That's how we do assignment of just value to a symbol. So we can check for equality, that thing is really just that list. And then we can mutate, well, we're not mutating, we're creating a new list based on the previous one, and we're changing the plus for a multiplication, right? So we have a list with the plus 2 and 3, and we're just saying we have a new one, multiply 2 by 3. And then if you evaluate the new one, you get 6. If you evaluate the old one, you get 5. So that's the idea. You can do lazy evaluation just built into the language. And this is how macros work. A macro is a function that takes a code, a list, and produces another list. And that's how you unlock all kind of meta-programming that is up to feature parity with all the other macro systems, and it's just simple. You can understand it in 20 minutes, and it's great. Okay, a lot of information. So let's talk a bit about BNF. BNF are the Backus-Naur Forms. It's a formal language to describe a type 2 grammar, right? A context-free grammar for a programming language. So most academic literature on writing parsers is using BNF. If you take the Dragon book, the compiler book, if you take a lot of information online, most languages don't have complex grammars, so you can just use BNF for that, and you should. If you're writing a parser and you just want to do the traditional thing, use this. You feed that language specification, like grammar, into a parser generator, like Yak or Bison, and it will produce a C or C++, whatever language program. That is your parser, basically. You can use that then to build the syntax tree for your code. And this works. It works great. Obviously, it has some limitations, right? So some languages, C++ is always a good example, it's too complex to be handled completely by this thing. So it's like C++, the templating system is Turing-Complete, right? So you can't handle that level of complexity with BNF. So what the compilers typically do is they use BNF to get a simplified version of the syntax tree, and then they just use code to traverse that and make sense of it, add semantics into that tree. Now let me give you an example of where things kind of break down. Is suppose we have an example here, like let is the way you do lexical bindings in Lisp. So I'm just saying x is 1 in this scope, and y is 2 in this scope. And that is valid, right? That is valid syntactically and semantically. But if I have an example where I just have plus x and y, and they're not defined, that will give me, obviously, a semantic issue where x and y are not defined. But if you write a BNF grammar to parse this code, to generate a tree from this code, you're going to get a tree either way. You don't know that those values are undefined until you try to apply semantics to the tree. So that's where it breaks down, basically. And in C++, you kind of have to add the semantics at compile time for the templating system, and that's Turing-Complete. So BNF can't handle that, and you need to use actual Turing-Complete code, regular code, to be able to handle its grammar. And so there is a saying that if you can write a proper C++ parser, you are already halfway to getting a C++ compiler anyway, because you had to deal with this stuff somehow. And this is part of the language specification. It can't be solved. I mean, it's just the way the thing works, and that's it. So it's impossible. It's not doable. So, okay, let me talk a bit about then the solutions to this issue. So this is like the worst case scenario. Let's try to solve the worst case scenario. And these libraries absolutely do that. So there is Boost Spirit, part of the Boost project, which Peter Simons told me about. There is Parsec and Tree Sitter. And there are other things. There are more libraries, but these are like the ones that caught my attention. So what they basically do is they allow you to inject code, arbitrary code, during the parsing process. So as you're parsing the code, you can do anything you want. At that point, you are in a Turing-Complete level, and you can implement the templating system, add the semantics, and do whatever you want. Boost Spirit is C++. Parsec is written in Haskell, so you kind of have to get into Haskell type theory, monads, algebraic data types. You go to the ivory tower to study for a few years, and then you come down pretentious and snob. It's inevitable. Tree Sitter is written in C. Tree Sitter uses 3 languages, actually. It uses C for its implementation, JavaScript for its grammars, and S expressions. It uses like a Lisp thing for its query language. So Tree Sitter is like a mixture of things. Tree Sitter is very efficient. Let's talk a bit about these things. So Parsec, the real goal of that is to say you're a functional programmer. You are already in your ivory tower or climbing, and you're like, I want to just write correct code from the get-go, and I want my algebraic data types. You are a Haskell or ML or OCaml kind of person, and you just say, I just want to use something that's familiar to that. Then you use that. Tree Sitter is if you want to embed this parsing stuff into like a text editor. You're writing an LSP server for some dialect, some language. You need the real-time performance. So it's really meant to be embedded or part of a bigger chain, a bigger pipeline. And it's very fast. So it's probably the fastest of the 3. And Boost Spirit is if you're a C++ programmer and you are in your other ivory tower and you just say, I don't want to leave C++, then good luck. Okay, so out of these 3 implementations, Parsec, being a functional language, Haskell is the one that's most similar to Wololo, and both are written in a purely functional programming style. And if you go and study Parsec, you're going to have to get into Haskell. You're going to have to get the Haskell book and the compiler and really sit down and think about stuff. And Wololo, what I'm trying to do is, if you are a JavaScript programmer, you're a Python programmer, a Ruby programmer, Golang, if you use something garbage collected and you just want something practical, that's what I'm trying to do. I'm trying to dilute the ivory tower into an ivory box, and then you say, here we go. There you go. You can pick that when you want on the go. And yeah, so I'm trying to say, let's embrace dynamic typing. It's not as bad. People say everything's going to be terrible, but no, it's not. I could have given some real examples of Lisp programs. If you have played Crash Bandicoot, any of the Crash Bandicoot games on PlayStation 1, The Last of Us on PlayStation 3, 4, and 5, These games made heavy use of Lisp, and they all run at 60 frames per second, and they are just amazing games. So, yeah, Lisp kind of pushes the boundaries, and which is cool. So, what is our approach then? Our approach is to have very simple data structures that you can kind of make sense of in half an hour. And we are trying to dilute this whole thing down to something simple. Using dynamic typing, garbage collection, performance is not our main goal. It's developer experience and being able to communicate this over a cup of coffee. So we have the AST nodes. This is how we represent them. We have types. They are arbitrary strings that you can assign to a node in the tree. You can add anything you want. Just add strings, and it has to be a set. Then a value is a string that represents the value of that particular node, and it's anything you want to, well, it's the thing you're parsing will produce a value. And then the nodes are the children that make this thing recursive. They should also follow the same specification recursively all the way down. And the moment you say, is a root node a valid node, it will validate everything recursively. And because Lisp has tail call optimization, you never run into a Stack Overflow. So in Lisp, you get recursion. If it's in tail position, you can recurse endlessly, and you never allocate more memory than one stack frame. So you have arbitrarily deep recursion. So we're not hitting a Stack Overflow. And so it's a very simple thing. It's just saying I have children and a value and a few types that you can annotate this particular node. And then we have a parser output. So a parser output is when you give it a parser is a function that takes some string and produces a node. And that's it. And then we have another data structure called a valid parser output, which is just saying, this is what's left to be handled. So let's say you're handling a substring of your string. You give it a whole string, and then it will only handle the first part of it. Let's say the int x, y equals y, comma. And so the parser has to be able to signal to the system what's left to be handled, right? It says, I'm going to handle this thing, this subset, and this is what's left. So next input is for that, is for saying this is the rest of it. The node is the node that you produced from consuming part of the input. And then you have the start position and the length where you handled. So let's say you handled the very first 3 characters. You say I started 0, I handled 3 characters. That's what I handled. This is the node. This is what's left. And that's what a parser should produce based on an input string. That's what it should do. If there is an error for some reason and you want to signal that, you just say, this is what's left. I've got an error, or multiple errors. You have a list of a vector of errors. And that's it. That's it. So we're breaking down the heavy types into simple data structures. Then we have, so as I said, by definition, a parser is a function that takes a string and produces one of those maps that pass this check, the parser output question mark. You can have question marks in Lisp as an identifier, very handy. Ruby copy from here, if you're curious. And then for now we have 3 functions: parse, exhaust, and best parse. So I'm going to talk a bit about them. What parse does is you give it a parser, one of those functions, a string, and it will just produce the same thing, and it will just enrich it with a result, saying, was this successful or is that an error? So you say result success, you're good. Result errors, you have errors. So that's basically that. It's just adding a little value so that you can check on the upper level of the code where your errors are, if there are any errors or if the whole thing was successful. Because if you have any errors, you have to find them and handle them. Exhaust applies a left to right, non-backtracking strategy to pass the input. And exhaust is where things start getting more intense. So let's say we have a number parser, and you can just imagine that it takes digits and handles that and reports that as the start and the length. And an operator parser is just going to handle basic arithmetic symbols. And then we say, if I give it an expression like 42 plus 3, we're going to get this AST. So you can kind of see the AST taking form here, becoming a real thing that you can traverse and add semantics to. And then he's going to say next input nothing, because it handled all of it. And it's going to say errors, no errors, success. And there is your tree. There is your tree with your type and the number, integer. So you can add as many as you want. You can say this is a number, but it's a float. This is a number, it's an integer, and the operator. And all of these values, they come from the parsers, right? So that info, this is a number, and it's an integer. The parser generates that thing. And then in case of a failure, you get syntax errors. Right now, you don't get the line info. You only get where it failed, but I'm going to add line and column and all that. So exhaust implements this left to right, LR parsing, non-backtracking, but we could add other strategies. So this is pretty extensible. Okay, so there is an algorithm, how exhaust works in detail. I'm not going to go over it. It's too much for 9 something in the morning. But there is a proper algorithm. So here is just an example again. Say we have some stuff in the middle that we can't understand. We're going to say we have part of the tree, so you can still make sense of that, but we get an error. And then we say the overall result is errors. So this is why result is useful, because you can say the overall operation failed. Here is part of your tree, and here are all the errors. So you can report them to the user and do whatever you want. Yeah, and because we are in Turing-Complete world where we can just use code to do anything we want, this whole thing will be extensible forever. There will never be any limitation. Let me just see. Yes, okay. So what are the goals actually for this thing is we want to make BNF, the language I showed you at first, a sub-language of this thing. So if you are already into parsing and you say, I know context-free grammars, BNF will be a subset of this. It will be a subset of this Lisp language that you can use. In the end, what you'll get is the library. If you use the library in Clojure, you'll get a Java file. Bear with me for a moment. So you'll get a Java file, and you can just run it anywhere you have the Java virtual machine. You don't need any dependency. You just have the JDK, and you just run that. That's your parser, right? You use the library, you build your own parser manually, and then you just get a jar file, and you can send that to your colleague and say, here, use this, and it will produce the tree for you. We are going to basically embed BNF in this library, the whole of it. The whole BNF thing will be in this library, so you can reuse your existing knowledge. I'll give you an example of that, how that might look. So yeah, we want to ease the transition. Then we're going to add transformers. A transformer is something that takes a parser output already, something that you already have an output for, and produces another one. So the idea here is you can use BNF for the part of the code that is context-free, if you want. And then if you want to add more semantics to it, you can take that as an input, write another level of Turing-Complete code now, because you have your whole Lisp language, and you can handle at that level then. So this is why we might say, let's use BNF for the regular C++ grammar, and then when we want to get to the templates, we would add that as another phase in the pipeline, let's say, for example. C++ is the worst example. So if we can handle that, we can handle anything. Not saying that the language is bad, just saying that the grammar is complex. So yeah, we want to add these transformers so that we have BNF plus Turing completeness in the same library. And we want to reach feature parity, really, but without ever requiring you to learn type theory and a lot of stuff. So we just want to have something that you can understand from examples, data structures, dynamic typing. Should be easy. Not for us, but for you. And then, yeah, we want to match the capabilities of those libraries. And something that I think would be really cool is to say, I want to take one of these trees. It should be trivial as well. Serialize that as JSON or XML, something that you can traverse from another language. So say you're a Python programmer, I give you a jar file to parse RPM spec files and do the macro expansion, do the whole shebang. Then I give you the jar, and you say, I can just use this now to parse any RPM spec file and get the JSON out of it. And then you use JSON path to traverse it and to handle it. You can just import JSON. There you go. Now, this should power, you can imagine how this would power a next generation of tooling around any kind of stuff that we want to do. Because now you don't need to write any more Lisp. You're like, okay, you use Python, Ruby, whatever. And further research. So there is more to learn and more to find. So I'm just going to give you a brief example of how we're going to go about embedding DNF in this thing. So we basically have to add all these common combinators and operators and things. Because Lisp has macros, this is an example, we can kind of create these macros, and they are special in the sense. You can think of a macro as a Ginger 2 template, right? If you're coming from Django and Python, you can think of it as a templating engine where you give it parameters and it will expand to the actual Lisp code that the compiler will then see and compile. So it's a lot like an RPM macro, really. So here is an example. That's the first example I gave you at the beginning. That's BNF. I know it's a lot less verbose. And this is how it would be in Lisp. One version. I can make this shorter. If I make this shorter, it's not going to be as easy to understand for someone who has never seen any kind of Lisp code. But you can see here I have the def rule macro. That's a macro. Then I give it a string. I gave it a string. I could just give it a digit without the quotes. Would also work just fine. So we can we could do it that way. It doesn't have to have so many literal strings in the code. But you can see how that digit, saying it's either 0, 1, and up to 9, translates to this. So you can say a digit is a choice between any of these. So you can see how the semantics kind of translate quite well. Then we have all these rules. It's basically a literal conversion of that to this. But we can write this in Clojure. And then you say exhaust. This is the name of the type that you want to give to the root node. Could be anything. And then you say, I want to reference. This is also part of the list of common operators that we need to implement. So you say, I want to reference that BNF thing, the root grammar, that one. And you want to say, and then that's the expression. So it's a direct conversion. This is BNF in Lisp. And from there on, you have Turing-Completeness around it. We could add more stuff, like we could add all these things. We could potentially, we're not going to do that, but we could. And this is what you would get out of it, right? Handling that. That expression, 2 plus open parenthesis 3 times 4. You would still get your AST nicely decorated, nicely typed success. So it's the same thing, really. It's just you're getting there through this BNF-like library. You don't have to write the parsers on your own. And that would be it, really. Are there any questions? Thank you.
Well, actually, I have one question. I didn't really understand that Lisp example, but
Okay, at the beginning?
Yeah, at the beginning, but that's probably for further study.
Go back here. Maybe that one. Okay, so the way it works is you can think that in Lisp there are no statements and it's only expressions. So everything you do produces a value. Everything everything produces a value. And this is like just an expression. You can read that line on its own without considering the rest of them. And what it's going to do is going to say, there is a plus there, right? It's going to say, let me find the actual function that is bound to that symbol. So the plus is not the function itself. It's just a symbol. It's just a reference, a name, right? And you're going to find that function. And you're going to say, now let me apply these parameters to that function. So it's like you're calling plus as if it's a function, really. It's not an operator. It's a function that happens to have the name plus, single character. And then you're saying, let me pass as arguments to that function 1, 2, and 3. So that's argument A, B, and C. Variadic parameters.
Like this slide is quite simple, but that next slide was.
You mean?
I got lost.
Here?
Yeah.
Okay. This is a bit different. So here I'm just saying that this symbol form is the value of that is going to be that literal list. Okay, because there is a quote there, that list is not going to be evaluated. We're not because if I remove the quote, the single quote, that's going to do +2, 3. That's a 5, and then it will assign the 5 to the form. But when I do the quote, I say no, don't run that. Just that's a literal list that I don't want to run as code. So don't treat it as code. That's what the quote does. It's just a little syntax, what part of the 1% of the syntax of the language. Then I'm just assigning that to this symbol. This could be anything. It could be whatever name we choose, X, whatever. And here I'm just proving that this is the same. They are the same. They have the same value. So form, which is that, is the same thing as having a list which contains the literal plus symbol, 2 and 3. So I'm just checking for equality to prove to you that this is the same thing in memory. Does that make sense?
Yeah, so this basically that parenthesis list slash +2, 3 means, would it be the same if I, instead of that, put there the thing which is above?
Yes.
Yeah.
It would be the same thing. Yeah. That's another way to write the same thing. This is a list function that you give it parameters and it produces a list without evaluating that list, without doing anything, just produces the literal. And here I again need the quote, because if I remove the quote, I get the actual function, not the symbol. Like I dereference that symbol and say, here is a function. And I don't want to add a function to the beginning of the list. I just want the symbol, because the evaluator will do the dereferencing of the symbol for me later when I do an eval, when I do this. So I can't have the function. Otherwise, I will try to dereference the function in the symbol table, and it's going to give an exception. Danilo, did I answer your question?
Like, I don't see why 0 would make a difference to that. Like, appended 0.
Here?
Yeah.
Okay, this is another, I should have used a better example. So here what I'm doing is I'm taking form, which has a plus, a 2, and a 3, and I'm saying at position 0, at the 0 index, change that to the multiply. So I'm producing then multiply 2 by 3 and assigning this new thing to new form. Okay, that's what I'm doing. I'm saying manipulating that list to change that to a multiplication symbol and producing multiply 2 by 3. And then what we do is we do eval on the new thing and we get a 6. And if we do eval on the previous thing, we get a 5. So I'm just showing how you can do lazy evaluation by saying, don't run this list now, just hold it, and then later we do eval. And this eval isn't dangerous because we're evaluating a list, not a string. So it's...
Perfect, thank you. I understand now.
Thank you.
So my question is, since Lisp is really easy to parse, would it be possible to embed a Lisp interpreter inside another language, like for example Rust, and use Wololo inside another language?
Yes. So Wololo right now is written in Clojure. It doesn't have to be. There are Lisps that are statically typed and not garbage collected and ready to be embedded in C, C++, Rust programs. So yes, we could write another like Lisp-like language in Rust. There is a project called Clojure Rust that is a Rust implementation of the Clojure language. It's not under very heavy development. There are other dialects like Scheme. There are other Lisps that you can embed GNU-Guile that you can embed very easily in native programs. And we could totally write this in that dialect of Lisp. It would not be hard to convert Clojure to that. And we could then embed that in Rust and make that part of a LLVM pipeline or something. Because then you get your AST, you can just convert that to LLVM IR, intermediate representation, and go crazy and do your stuff there.
Thank you.
Yeah, you're welcome. Thank you for the question.
Yeah, so my question is, can you handle the Unicode monster?
Yes, because the language can handle the Unicode monster. So we could fairly easily. So Clojure runs on Java. it runs on the common language runtime from Microsoft, .NET C#, that VM, and it also runs in JavaScript. You can compile Clojure to JavaScript and run it in your browser because it's it's been done. So people are doing that. There is a bank in Brazil called Nubank. Not sure if you've heard of it. It's a multi-billion-dollar bank. It's the largest bank in South America, I think, or one of the largest ones. And all of their stuff is Lisp, is Clojure. So it can handle very much heavy real-world applications, and we can handle Unicode just fine. Mostly because the strings in Clojure are Java strings. So as long as the JVM supports that, we can just get that for free.
Thanks.
Yeah, thank you. Are there any more questions? Okay, I think I'll give you a few minutes. Thank you very much, and it was a pleasure. Thank you.